In this lecture, I'll talk about the quicksort method, the last of our sorting methods. So we've looked at bubble sort and selection sort, there are linear methods. We've looked at merge sort, which is the divide and conquer method, and then quicksort, which is the last of our divide and conquer methods. So quicksort. Quicksort is considered one of the most important algorithms of the 20th century. It was created by Tony Hoare in 1959. Why is it so good? Why is it so important? We've talked about this before. Sorting is really what search engines are doing. It's actually a lot of work is sorting things into lists. Now, how does quicksort work? So if you have a list of numbers, what it does is, so there are many different ways of choosing pivot. The one I'll talk about here, and I'll talk about a different one later, is you take the first number, the middle number, and the last number. And what you do is you find which of them is in the middle. Okay. And here, the first number is 5, the last number is 1, the middle number is 2 in our list. And then we say, okay, everything should pivot around the middle number. So the pivot is 2, we have our list. And what we ask is we move our way along and say, is 3 less than 2? No. So it stays where it is because it's on this side, because it works its way down one way and works its way up the other way. So it divides them into two lists. One list which is less than 2, one list which is greater than 2. Note this list isn't sorted, but everything in that list is greater than 2. So then we do the same thing again, but we pivot these 3. And here, when you pivot 3, it just puts them into order 3, 4, 5. And that's how it works. So let's do a longer example, but with words. So we're going to use a quicksort to sort the word sorting. So first we define our pivot. Our pivot is what splits the two lists. So our first letter is S, middle letters T and G. So our pivot is S. So that means we put G at the front and T at the back. And then we work our way along to say, is O in the right place? G is gone, so it's N less than S. Now N will have to move. So it has to switch to OR. It finds the next one that isn't less than OR, less than S, and flick it. So O, so we start here and move our way down and move our way up. So O moves. O stays where it is. OR is less than S, so it stays where it is. I is less than S, stays where it is. N is less than S. So like before, our pivot wasn't very good because if it's a good pivot, we'd have split 50-50, but we didn't. Now, we do the same thing again, but with the long list here. G is our first, OR and N is the middle. So G and OR get put in their rightful places and we work our way along. So now we ask, is O less than N? No. Is I less than N? Yes, so I should be put here and O should be put here. Yeah. And O, and then we're done. And N goes in between. Yeah. So now this list, all of this is less than N, all of this is greater than N, and all of these are greater than N as well. So now we have GI, N, O, or ST. Gin sort. So, like with the merge sort, you split the list, you split the list again, you split the list again. But how you choose to split the list and how much effort you go into splitting the list is the difference between quicksort and merge sort. In quicksort, you just put things together at the end, they just combine nicely. The effort is when you split them and say, oh, who should be on which side of the list? They will not be ordered when they get placed, but who will be on each side. Now, how long does it take to do the quicksort algorithm? In the worst case, and actually 2 examples I have are the worst cases. When it splits, you don't have to do any operations on one list and you have to do n-1 next, split again, split again, split again. So the longest case scenario is Cn to n minus 1, which is n squared. The best case scenario is every time you split the list, it actually splits nicely on the pivot. Half the list goes to the left, half the list goes to the right. And this is n log n, like the merge sort. So our pseudocode. Now, because quicksort is recursive, as in it keeps using itself again and again and again, we define something called quicksort that takes in a list, and it says which is the first element and which is the last element. And then we have quicksort helper. And this gets where it gets interesting is quicksort helper. First it checks is first, last, and last. So are we finished our sorting? Then it splits the list using a partition, but then it feeds it back in. So now what happens is this does the left side, this does the right side, but it feeds itself back into itself. So it keeps on doing that splitting until the first and the last are the same, as in you have it sorted. Now the partitioning is where all the work is. In my pseudocode here, I just take the first one as the pivot. So then I go, the left mark is the first plus 1, the right mark is the last. Done is equal to false, so that means you're not finished sorting, and then you split. And all it's doing is it's working away along from the left side and from the right side and putting them in their appropriate list, in the left or right list, and then it's done. So you need these 2 bits of code to do the quicksort. The flowchart could be very complicated, but I decided just to go with the simple version of it. You have your list, you choose your pivot, you partition your arrays into 2 lists. If it's sorted, you move on. If not, you split those 2 lists into lists, find our pivots, go round and round and round and round again. So that's the quicksort algorithm. I'll be doing a longer example in class to get you more used to it.